Here we see the ram air turbine in the context of the aircraft. The first thing I'm going to do is use Creo mechanism dynamics to find the loads that this green mounting bracket are subjected to. We use mechanism constraints to form the joints in the assembly. The analysis results gives us the loads that are transferred into the bracket through the pins. As the analysis runs, you can see the force vectors represented by the magenta arrows. Once we know the maximum loads, they can be transferred into the structural analysis in Creo Simulate. Here we select the loads that are important to us and transfer them into Creo Simulate. Looking at just the mounting bracket, we run a static structural analysis to see what the resulting stresses and deformation are. In this case, the maximum stress is at one of the mounting holes. And the maximum deflection is at the uppermost pin. We now have all of the information that we need to set up our generative design analysis. Here we have a multi-body part in Creo that we will use to define our generative design analysis. These bodies include volumes for design space, pins, attached locations, and exclusion volumes. We now select the generative design application. First, we designate a design space for the analysis. Once selected, it turns transparent. Next, we select the volumes that represent the preserved geometry. These are volumes that we don't want the optimizer to change. Once defined, they turn blue. Now we define the excluded geometry. This is a volume where we want to avoid placing any resultant geometry. Next, we add the loads and boundary conditions we used from before. We fix the lower attach points. We define contact between the pins and the preserved geometry, the blue rings. And we apply the loads to the pins. Now we can define the design criteria for the analysis. We can specify the target volume percentage or the target mass. We can add additional constraints such as manufacturing strategies like milling, molding, or additive. Here we've added a material property and additionally a symmetry constraint. We now have all of the information we need to run the analysis. As the analysis runs, we get real-time feedback on the progress of the geometry creation. This allows us to assess the validity of our analysis setup. In the upper left-hand corner of the graphics window, you can see the analysis statistics, including the current step and the current mass of the design. We can watch the progress of the analysis. The support structures are thickening in certain areas, thinning in other areas, and we can rotate the model and watch as the analysis progresses. Once the analysis is complete, we can take a look at some results. First, let's have a look at the von Mises stress plot. Here we see the maximum stress has been reduced by 68%. Now that we have an acceptable result, we reconstruct the generative body into a BREP solid. This step automatically wraps the body in a freestyle surface and solidifies it. The resulting solid model can be easily modified. Now that we have the reconstructed BREP solid model, we can use Creo Simulate Live to validate the analysis results that we saw earlier in the Generative Design tool. Now we prepare the model for additive manufacturing. The first thing we want to do is run a downscan analysis to find the optimal orientation for the model on the build tray. Here we have positioned the part on the build tray in the optimal orientation, and Creo has generated the required support structures using materialized magics. We can preview the model before printing, perform print validation checks, and print directly to connected printers. If your printer can read and use slice files, Creo can create and display the layers used for printing. Here we see the slices displayed on the model. Going back to the design space used to produce the generative design, we can add a manufacturing constraint for 2D machining. The result in this case are two separate parts that can be easily machined. Reviewing the generative design criteria, we have added a linear extrude constraint relative to the central datum plane. After reconstruction, you can see that these parts could be machined with a variety of conventional methods, like water jet or milling. Because we are working with Creo, we can make modifications to the resultant geometry, either by modifications of dimensional values, if available, or by using the flexible modeling capabilities in Creo. Finally, we can quickly check the structural performance of the design by turning on Creo Simulate Live at any time to get instant analysis feedback. In the past few minutes, we have derived the load case for a new ram air turbine mounting bracket, generated an optimal design based on weight and structural requirements, automatically constructed a BREP solid model from the results, verified the structural performance of the design, and prepared the new design to be additively manufactured, all within Creo Parametric.